You ever write a line of code, or heck, even just type a sentence, and stop and think, what's really going on under the hood? Well, today, we're going to pull that curtain all the way back. We're going to see exactly how a computer takes a simple command and turns it into pure action. Let's dive in.
All right, let's start with something that probably looks pretty familiar. It's a basic instruction, right? Written in a language that we humans can totally understand. We're telling the computer, take a number, x, add another number, y, then subtract a third number, z, and just save that final answer. Seems easy enough.
But here's the catch. At its very core, a computer is really just a massive collection of on and off switches. It doesn't get words like result or symbols like a plus sign, so how on earth does it get from our nice, clean instruction to something it can actually work with? That's the big question we're tackling.
So the first thing you got to understand is translation. It's just like trying to have a conversation with someone who doesn't speak your language. You can't just talk at them. You need an interpreter. Well, it's the exact same thing with a computer's processor.
So check this out. This is that first layer of translation in action. Our one simple line of code gets broken down into these smaller, more basic steps. This is called assembly language. Instead of one big idea, we now have a very specific to-do list. First, load the value of x. Then, add the value of y to whatever you've got. Next, subtract the value of z. And finally, store that result. It's way more literal, right? We're getting much closer to what the machine actually needs.
Okay, so we're getting warmer, but we're not quite there yet. I mean, words like load and add are still, well, they're still words. And as we've already said, computers don't speak English. They speak math, they speak numbers, which means there's an even deeper layer we have to peel back.
And this is it. This is machine code. This is the processor's native tongue. Every single one of those assembly commands corresponds to a unique number. So load x just becomes 1006. Add y is 3707. This is what the computer actually sees. Just a long stream of numbers telling it exactly what to do and where to find the data it needs. All the amazing complexity of your software, it all boils down to simple numeric codes just like these.
Okay, so the computer has its instructions, and they're all numbers. But who or what is actually doing all the work? For this, let's imagine the CPU. The central processing unit is like a super fast, hyper-efficient little workshop. And inside that workshop is a small team of specialists, and each one has a very, very specific job.
First up, meet the foreman of our little workshop. This is the program counter, or PC for short. Its one and only job is to keep track of what's next on the to-do list. It holds the memory address of the very next instruction, making sure the whole operation just keeps humming along in perfect order, one step at a time. It never loses its place.
All right, next up we have the loading dock. This is the memory address register and the memory buffer register. You can think of the MAR as the forklift driver who knows the exact aisle and shelf number in the warehouse, that's our main memory, where everything is. The MBR, that's the loading bay itself, just a little temporary spot where data and instructions hang out as they're coming in or going out.
So, once a new instruction gets dropped off at the loading dock, where does it go? It goes straight to the instruction register, or IR. Think of this like the big whiteboard in the middle of the workshop. It holds the one specific instruction, that numeric machine code we saw, that the entire team is focused on at this exact moment.
And now, for the main event, the star of our show, the accumulator, or AC. This right here is the workbench. This is where all the actual work gets done. When we need to add numbers, subtract them, or do any kind of calculation, it all happens right here on the accumulator. It is truly the heart of the whole operation.
So we've met the whole team. Now, let's put them all together and see them in action. We're about to watch the fundamental three-step dance that every computer performs billions of times a second. It's called the fetch-decode-execute cycle. Okay, to really get this, we're going to zoom way in on just one single command, load x. Its machine code, as we see here, is 1104. Now, this number actually tells the CPU two things. The 1 at the beginning means load, and the 104 is the memory address where the data for x is hiding. So let's watch the team handle this one job.
First up, the fetch phase. It all starts with the foreman, the PC, pointing to the next instruction's address. It hands that address to the MAR, our forklift driver at the loading dock. The MAR zips over to that address in memory, grabs the instruction 1104, and drops it in the MBR, our holding bay. Then that instruction immediately gets moved to the main whiteboard, the IR, so the whole team knows what's up. The instruction is now fetched.
Okay, next up, decode and execute. The instruction 1104 is on the main whiteboard, and the team gets it. The 1 means load, so now they know they need to grab the data from address 104. That address is sent back to the MAR, who goes and finds the actual data, in this case, the number 35, and brings it to the MBR holding bay. For the grand finale, that data is moved from the bay directly onto our workbench, the accumulator, and just like that, the command is done.
And get this. That whole dance we just described, the foreman pointing, the data moving from the warehouse to the loading dock to the whiteboard to the workbench, all of it happened in a fraction of a billionth of a second. It's just mind-bogglingly fast.
But, computers do more than just follow a simple checklist, right? Their real power, their magic, comes from being able to make decisions. So how does our little workshop handle something more complex, like an if-then statement?
Well, check this out. On the left, you see a basic decision we all understand. If X is less than Y, do one thing, otherwise, do something else. But how does a CPU, a bunch of switches, actually make that choice? Well, on the right, you can see the clever little trick. First, it just does a subtraction, X minus Y. Then it uses this special command, SKIPCOND. This command looks at the result on the workbench. If that result is negative, which means X really was less than Y, it does something super simple. It just skips the very next instruction in line.
So, let this sink in for a second. A computer makes a choice by turning it into a math problem. That's it. Is the answer positive, negative, or 0? And based on that simple result, it either follows the next instruction or it literally just jumps over it. Every complex app you use, every video game, it all boils down to this incredibly simple, elegant idea of doing math and maybe skipping a step.
So we've gone on quite a journey, haven't we? All the way from a single line of human-readable code down to the microscopic ballet of data happening inside the CPU. We've seen how these incredibly simple, one-at-a-time steps, when you do them at unbelievable speeds, can build up to create almost infinite complexity.
And what does that unbelievable speed actually look like? Well, a modern processor can run that entire fetch-decode-execute cycle about this many times. 4 billion times. Every single second. That's the absolutely staggering scale we're operating on.
So the next time you click a mouse or type a single letter, just remember that little workshop inside. Remember the foreman, the loading dock, and the workbench, all performing that 3-step dance. Because if one tiny instruction involves all that work, just imagine the sheer miracles happening inside your machine right now. It's a powerful reminder that sometimes the most complex things in the world are built from the simplest ideas, just repeated at a scale that's almost impossible to imagine.